Welcome everyone to another episode of In a Nutshell, the fortnightly podcast hosted by Natural Gas World, where we look at the global news and trends in the gas industry. My name is Joseph Murphy, and with me today is Mich Hein, CEO of Germany's Electrochaea, to discuss a proprietary bio-methanation technology that the company has developed. The process involves taking CO2 produced by an anaerobic digester and green hydrogen to produce synthetic natural gas that can help decarbonize difficult-to-abate industries and serve as an energy storage. The technology has gained serious attention, with Electrochaea recently bringing on board international oilfield services provider Baker Hughes as a lead investor. Hi, Mitch. Thanks for joining us.
Hey, Joseph. Great to be here. Thank you.
So I hope my very brief summary of your technology was more or less accurate, but maybe for the benefit of our viewers, you could walk us through what the technology does and its various steps for the benefit of our viewers.
Great, happy to do so, and it's a pleasure to be here. So you mentioned correctly, the biomethanation is the core of Electrochaea's technology, and the focus, of course, for us is the hard to abate industries that are using right now fossil gas, where we think renewable gases are going to be an important part of the future. And so our technology is based on a microbe, which seems a bit odd because the biggest barrier that we see to hard to abate industries is actually being able to do this at scale. And so we need to scale a microorganism to macro scale. And that's been what our primary goal has been, to develop a system that will do that. And principally, it means to develop the ability to use this microbe, which looks like a bacterium, but it's not. It's a little tiny rod. It's called an archaea. But to have that operate in a system with sufficiently high energy density that you don't need a huge footprint in order to work at scale. So that's typically what our system did or does. And what we do is we take green hydrogen and we take carbon dioxide from essentially any source. We can also use, as you mentioned, biogas. We can use raw biogas, so you don't have to purify the CO2 away from its inherent components like methane or hydrogen sulfide. And we literally bubble the hydrogen and the CO2 into the bottom of our reactor, which is a vertical pipe. It's quite simple. It has an agitator in it in order to mix the gases in solution with the microbes that do one thing. They gobble up hydrogen, they combine it with CO2, and there's three products: a little bit of heat, water, and methane. And by the time the bubbles reach the top of the reactor, we have essentially pure methane. So maybe a small amount of some unreacted CO2 or hydrogen, but usually very low, 97, 98% methane in the product. And of course, it's, as you might imagine, this is in water, so it's soaking wet gas. So you've got to dry it before you can deliver it to the gas grid or to its use. So it's really quite simple. The organisms do the hard part.
And you have a plant in operation. That's correct, right? It's been in operation for quite a few years now.
Right, we have two plants that we've operated. One in Denmark, which we actually started operating in 2016, and we ran that one until early 2020. It's now we could turn it back on again. It's getting ready to be deployed for another opportunity, so it's not operating. And another plant that we ran in Switzerland that we built with funding from the European Union Horizon 2020 program. It's a larger project called Store and Go that compared several methanation technologies, and we ran that plant for about 8 months under the terms of the grant demonstration, and now we've moved that plant to Germany, and we're getting ready to set that one up and run it again in Pfaffenhofen, Germany.
So this is one way of decarbonizing the gas grid, right? But there are other solutions to that. Part of your process is producing the green hydrogen. That in itself can serve as a means of storing energy. That in itself can be put into the grid to help decarbonize it. You also mentioned biogas. That too can be put into the grid. What are the advantages of your technique in terms of reducing the carbon footprint?
Great. So on the great question, and on the back end of this, the decarbonizing the gas grid, of course, is our goal, and
Hmm.
it's something that's been done well with the power grid at this point in time by displacing some fossil assets. And so our goal is to displace the fossil-based methane that we're seeing in the gas grid right now with as much renewable gas as we can. And you're
Hmm.
right, it's possible to put hydrogen into the gas grid. You can put probably not biogas, but you can put methane that's been purified from biogas into the gas grid. There's some town
Yeah.
gas grids where you can put biogas in it, but the larger natural gas system really requires methane of relatively high purity. And so you can
Hmm.
do that by, for instance, removing the CO2 from biogas. In our case, we simply take that raw biogas that's, let's say as an example, it's 50-50 methane and CO2, run that through our reactor, and you have 100% methane coming out the top. So we provide a similar purification function, if you will, to the methane in the biogas, but we double essentially the amount of gas that comes out, and there's no then emission of CO2 from the biogas production source. The energy that we need to turn that CO2 into methane needs to come from a green source. In our case, we're using green hydrogen. And
Hmm.
in most of our current applications that we're looking toward developing commercially, that green hydrogen is coming from an electrolyzer that's running on renewable power. So that provides a connection then to the second part of the renewable energy platform, which is wherever and whenever we can find renewable power that is either underpriced or that is unwanted and otherwise would be curtailed or couldn't be easily stored, we're able to put it
Hmm.
into the chemical bonds of methane and put it into the gas grid where it's available for use at any time and any place that's connected to the gas grid. So we're affecting a method of storing energy and redistributing it, and we're displacing, of course, a fossil methane molecule every time we do that. So that's the overall objective that we're after. And to be able to do that at
Hmm.
scale means we need large quantities of CO2 and large quantities of renewable hydrogen.
Hmm. And methanation isn't exactly a new technology, so it's been in use for decades. So what makes your technological process stand out?
Right. So what makes ours stand out is it's actually older than the technology that's been in play for decades. I mean, chemical
Hmm.
methanation using metals and metal oxides is, at high temperature and pressure has been around for over 100 years. It's a basic Sabatier process. It's well known. It's been commercialized. It's quite sensitive to contaminants, which is one of the advantages that our system has, and it tends not to be overly flexible in terms of duty cycle. So
Hmm.
what makes our system different is that we're able to operate at relatively low temperatures and pressures, which means that duty cycle on and off and changes in flow rates are relatively easy to manage. There's an
Hmm.
esoteric piece of the microorganisms that, from a chemistry perspective, that makes them more amenable to multiple duty cycles, and that is, since it's not a chemical reaction that occurs with a bunch of intermediates in a reaction pot, it's a
Hmm.
concerted reaction where there's a bound CO2 molecule that's simply reduced with 4 2-electron transfers to yield methane. There's no intermediates. So when you turn it off, you stop the process with no intermediates around. When you turn it on, you make a product with no intermediates. So that's what makes the process different. But this process has been around in these organisms, the archaea, for people reckon onwards of about 3 billion years. They were the first methane producers on the planet. We just happened to have found in a laboratory at the University of Chicago a strain that was developed by Dr. Lori Metz that is phenomenally inefficient for itself, which means it's really efficient for us. So the
Hmm.
clever piece of this is it's an organism that sits in this tank, but it makes very little of itself. Only about 1.5% of the carbon and the energy that goes into the system goes to make or maintain the organism and maintain the catalyst. The rest of it turns into product. And for most fermentation systems, the opposite is true. You get very, very small percentage of the product and you get a lot of biomass. In our case, we get very, very small amounts of biomass, and we're able to operate this system with high energy efficiency and high yields of carbon dioxide and methane.
Hmm. And to what extent is your process can it be viewed as carbon neutral?
The process itself is determined in its neutrality based on any basic life cycle analysis. If you put garbage in, you'll get garbage out. If you put electrons into the system, or green hydrogen or blue hydrogen that have very, very low carbon index, you will get a product out that has a very low carbon index. As you know, there are philosophical, religious, economic, and regulatory say values that are placed on the sources of energy and also the sources of CO2. And so in the economic environments that we're working, there are some sources of carbon dioxide that are regarded as having higher value because they come from biologic sources. And there are some markets where if you make CO2 from a geologic source, even though you're ultimately carbon neutral in your life cycle analysis, you still won't get economic credit because the carbon didn't come from a biologic source. So the neutrality of the carbon and the actual carbon index that you calculate is only going to be determined by the source of the energy that you have and how efficiently you run the process. Whether or not you get credit for that in any kind of regulated market is really going to be determined by the specific regulations in your political geography.
Okay, and obviously, I mean, at what kind of stage are you with the business? How would you describe your phase of development? And also, as I mentioned, you formed this recent partnership with Baker Hughes, bringing on Baker Hughes as a lead investor. What does Baker Hughes really bring to the table to your business? And are you looking for other strategic partners like that, which is to say partners that are bringing more than just funding?
Yeah, great question. I mean, I think the two parts of your question converge on the same answer, and that is the stage of our business is really, we have, from a venture capital based business, which is what we are at this point in time, secured several strategic partners who have helped us align what our overall business objectives are with what the market needs are, which is to decarbonize the gas grid at scale. And so we're at a position now where we've de-risked the technology internally with venture capital over the last 6 to 7 years, and we need to move to scale in order to meet the market needs and to meet customer needs. And so the Baker Hughes partnership for us is a watershed event in that we now have a partner that is integrated throughout the value chain, has the ability to scale in the market, and can work with us to make sure that we can accelerate our development at scale, but also avoid, having to, I would say, have our investors, of which Baker Hughes is one, but have our investors pay for us to come up the learning curve. Because what Baker Hughes and our other two strategic partners, who are Energy 360 Glad, who's a utility in Switzerland, and Storengy, a division of Engie, they can help us avoid, I think, what would be the pitfalls of a small company that is moving from a technology stage to a commercial stage. So that for us is key. So it's clearly the insight, but we're working with Baker Hughes in a partnership to actually scale carbon capture technology linked with methanation to be able to deliver gas to the grid at gigawatt scale instead of megawatt scale, which is where we've been working. So we're literally talking about a partnership that will give us a 3-log increase in our capacity to be able to deliver gas to the grid.
And of course, it might be a premature question, but presumably you have developed some sort of cost ranges for how much it would take to produce this synthetic gas.
Right. So the answer is, obviously yes. I mean, we've operated 2 facilities at megawatt scale for multiple years now, and we understand a good bit about the operating costs of a system at that scale. We understand also the cost of construction and delivery of a methanation system that's of our design, which is, as I said, this pipe. It's a relatively simple technology, so the scalability of it is quite good. I mean, it literally has only 3 rotating parts in it. It's you think about it, it's a crock pot with an egg beater in it, a pump to take the heat out of the system and a compressor to blow the gas in. So the scalability of that we think is quite good, and one of the reasons we're excited about our partnership with Baker Hughes is that they, of course, have been in this business for a while, and they have scaled technology that is supporting the market right now. So they understand more about the costs of these projects at scale than we do. But we think that the cost of a methanation system will be less than the cost of the generation of the renewable hydrogen at this point. The cost points will be lower for our system. And
Right.
the operating costs in the system at the end of the day will simply be the price of the power and the cost of securing the carbon dioxide. Those are your two main costs.
Okay. Do you have a number I can cite there?
Sure. It's a floating scale. I mean, there's no absolute number,
Yeah,
but
of course.
everybody wants to know. So it all comes down to system efficiency. So if you take renewable power and you make renewable hydrogen from that with an electrolyzer, you're getting about maybe 70 to 75% yield. So you've increased the price of the energy that you're running through the system by a factor of about 1.4 to 1.5. Our system operates at between 75 and 80% efficiency. So you multiply 0.8 times 0.7, and the overall energy yield efficiency from your system from start to finish is going to be between 50 and 60% yield out in the methane price. So if you pay 50 cents a kilowatt hour for your electricity, the cheapest you're ever going to be able to sell your gas for is $1 per megawatt hour. So it's going to be completely driven by the cost of the power that you have, and if you have also a cost for CO2, which right now is quite low. So what I would say is, if you want to build this business in a way that you're creating value for your investors, the real value that you're generating is the value in what we would call the carbon attribute value of the gas. So you know what your energy cost is. It's basically twice what you had to pay for it. So the value that you're getting in addition to that is the value of having taken carbon dioxide out of the system, out of the release from the carbon, or release of the carbon into the atmosphere. And if that's $25 a ton or $30 a ton or $100 a ton, you will be able to receive a part of that carbon attribute value as part of the fuel value that you're selling as a renewable gas. And so in today's world, that might be maybe $15 a million BTU in the U.S. market. So $15 an MMBTU might be the current cost or the price for generating renewable natural gas. As the cost of power comes down and as the system scales, you could drop that cost in half. So that roughly those are the range that we're talking about. If you compare that to current markets in, say, California, where the renewable gases that are being sold into the transportation market with the California Air Resources Board LCFS system, the prices are a multiple of the one I just told you about. I mean, you might be in the, in some markets, even in Sweden, you might be in the vicinity of maybe 100 to 120 euros per megawatt hour for the renewable gas. So those are the benchmarks that you're looking at today. I don't think in the long run it'll cost that much, but I think it'll be somewhere between probably $7 and about $15 an MMBTU in future markets.
Okay, and in the past there has been quite strong movement in Europe towards the promotion of full electrification. I think there's been a recognition in recent years in Europe that might not be all that realistic. What's your view on that? Why do you need to decarbonize the gas grid? Why not simply electrify everything?
Well, I think the simple answer to the question is, if you want to electrify everything, you probably have to decarbonize the gas grid, because somewhere between 30 and 50% of the energy that you put into the electrical system is coming from natural gas. So you have to replace that. And right now there isn't a really good replacement for that you can do at scale. You're in a situation where if you want to do that all with renewable electricity generation, that's a bit of a daunting task. But when you want to turn your toaster on and the sun's not shining or the wind's not blowing, you have a hard time getting that power available to you. And batteries that can efficiently, from an economic perspective, store energy for 4 to 6 hours won't
Hmm.
provide sufficient buffer, and there may not be enough lithium available to do that at an affordable cost. So the best reservoir that we have, both for energy storage, but also for providing reliability and durability of our electrical system, is actually the natural gas grid and the gas to power, peaker plants and baseload plants that we have that are distributed in most of the developed countries in the world. So
Hmm.
the backbone of the current power generation system really is the natural gas system, and I think that most people that that love renewable power, as I do, don't realize the critical role that gas plays in maintaining the stability and resilience of that gas grid, or rather of that power grid.
Hmm. And you mentioned, so I mean, where would be the best places to deploy this technology in the world? Um, so you mentioned one factor is, an abundant supply of cheap renewable energy. What places are suitable?
Well, I mean, obviously the offshore wind developments, I think, are looking pretty to be pretty important for future development of large scale renewable electricity. I think in Europe and in North America, where the markets are developed or already and are developing more quickly, I
Hmm.
think areas that are provided with an abundance of solar energy will become those production areas, because they're close enough to the transmission and distribution networks for power for the major metropolitan areas that you'll see
Hmm.
it being developed there. I see certainly a push to do this in China, and in parts of northern Africa, where there are certainly solar resources available to develop a lot of renewable power. But I think you'll also see distributed renewable energy generation assets showing up in most countries that want to move to either to electrification or to decarbonize their overall energy sector. I think it's going to be everywhere.
Hmm. And if you were talking to a gas company, um, no surprise, we're natural gas world. A lot of our subscribers are in the gas industry. Should they consider this kind of technology a threat or an opportunity?
I mean, I would think they would see it as an opportunity, and in most of our conversations, they see it that way. I mean, I think that the price of renewable energy on the gas side is going to be higher, than fossil gas for a while to come, and so there's an
Mhm.
economic challenge to that. But the gas infrastructure that we currently have, as I mentioned before, is the backbone of much of the power industry that we have. But it also supplies significant energy to our industrial and commercial customers, for homes, for restaurants. It's a really critical component of the backbone. And the
Mhm.
existential risk to removing the gas grid for gas utilities and gas companies, I think, is serious.
Mhm.
And I think we need to have a probably an adult conversation overall to say, gosh, this infrastructure is one of the best investments we've ever made. It's
Mhm.
incredibly efficient at distributing and storing energy, and that energy could be renewable. Why don't we stop hating the system because it's a fossil system, and obviously contributing to some degree to our climate uh, gases, and think
Mhm.
of it as a way to distribute renewable energy. And if we do that, we can change the gas without having to change the business models and without having to change the infrastructure that we have in place that already efficiently uses that energy source.
Mhm.
So our conversations in North America and in Europe, which is largely where we've had those conversations, have been very positive. The issue has been scale and price.
Mhm. Now, your technology, obviously, you're using the CO2 to make an energy source. Another another solution to decarbonizing energy, which I didn't mention earlier, was of course carbon capture and storage. So that's another option available to industries. Taking the carbon and putting it away somewhere. Again, why do you think it's better to utilize the carbon than store it away in the North Sea or elsewhere?
So I honestly think we have to do both. And so what I would say, what's better probably is determined by what the application and the need is. So, currently the carbon is what our world is made of, and it's not going to change as long as, we're on this planet. You and I are made from carbon. Most of what we do is made from carbon. Our food sources are all made from carbon. The carbon dioxide cycle is real. It is the planet. And so we will be using carbon-based materials, and we are a carbon-based material for a long time. So using carbon as a backbone for what we do is what most of our chemical industry is about, obviously, not just the fossil fuel industry. So finding a way to use carbon well and to recycle it in a circular economy, I think, is key to sustainability. If you put it all in a hole under the Atlantic, you're not going to have that carbon available to reuse it. But if you're generating it in those large quantities, first of all, the cost of it is dropping. So now it's available as a resource. And if you can use it as an energy carrier, if you can use it as a component of carrying value in chemicals that have more than their energy value because they're building blocks for what we do, using that carbon as a resource is, I think, incredibly important. And we already do that, of course, with everything that we do that's plant-based. All of our plant-based materials are based on carbon that is fixed from the atmosphere by plants, and they're using solar energy to do that. So we're just learning a lesson from the plants that are around us about how to better use and recycle carbon dioxide. So I think it's both. And I think that, if we're going to reduce ultimately the amount of CO2 that we have in the atmosphere, right now we're trying to reduce the rate of release, but if we're actually going to get that number down, some of it's going to have to be stored, whether that's underground or in mineral form. We'll have to get some of it out so that there's a net negative flux of carbon dioxide out of the atmosphere.
Okay, any closing remarks?
This is the first time I've had an opportunity to have a platform to speak to the gas industry. So I think from Electrochaea, we would say we think we have got a great potential product for your customers. It's the same product that you sell and distribute already. We just happen to make it by a different method, and we're scaling up, and we hope we'll continue doing business with you.
Okay, thank you very much. So this has been another episode of In a Nutshell, the podcast hosted by Natural Gas World, where we look at the global news and trends of the gas industry. Thank you, and see you next time.
Thanks, Joseph.